So we can start. Let me share my screen. Today we are going to talk about recursions and functions. Right. So feel free to talk and answer questions and anything, because we don't really have many people now. That's okay. Let's start. So I assume that we already know like functions. Is it true? Yes. So that's why we're not going to talk about functions that much. Just some, let's say, tips or things to know. But before that, let's very briefly cover function. So function is a thing like that you write programming, right? For example, the main function, and then other than the main function, we can have other functions. I don't know. I'm just gonna like very briefly cover the function thing, and then for example, let's say function 1. So the structure of the function, like the syntax of the function, is that we have the type of the function, as for example void. It can be int, double, I don't know, pair, and then like so on, and many things like long, and blah blah. And then we have the name of the function, right? And then we have the arguments part. We have the arguments part, as for example, we declare what arguments our function expects, like int n, vector a, right? And then we have the body, which is starting from here, and then here you write the body over here. And basically function is a mini program in our code that that runs when we call it. To call a function, we do like we write the name of the function, like function 1, and then we give the arguments necessary, as for example like 5, v, and so on, and then we get returned the type of the function. This is the return type, right? So in case of void, we don't get anything. In case of int, for example, we get number, and then for example we can assign answer equal to the function number. So let's see. So as we briefly covered about the function, what is functions, like the syntax, I mentioned, for example, argument vector. Any ideas about this? Is there anything we should know, for example, when we do like a function in vector int b. No. So Duman Question to you, for example. Should we be careful about something over here? As we write vector, we pass a vector as an argument, like cout function and then like we put, for example, int. This is in the main. And then we pass the vector. Yes, exactly. The problem with this is that it copies the vector and gives to the function. Basically, if we, yes, the vector can be very large. Basically, when we do this, the whole program creates another vector, copy of the same vector, and it passes through here. And it takes O n time, where n is the size of the vector. So if you work with big functions, it's gonna be very, very long to do. As like imagine passing every single time. Like you write a function, for example, like you have an array of vectors, which is going to be like vector int the 100,000. An array of vectors. So, and every single vector have, for example, let's say the size is equal to, again, 100,000. And then you have a function. You try to organize your code in some way, and you want to create a function where, let's say your function changes some element x in a vector e. It changes, it returns, like it does cout, and that's it. Like, I don't know. For example, like void, or just prints, basically, just prints, yeah. Function, func, int x, int e. And because the vector that you want to access is local, it's not a global variable, right? So what we do, we also pass the vector so we can access it, right? And then we just see out like it's. But then the problem is that every single time, if you call it like 100,000 times, and then what's gonna happen is that it is going to be very slow, because every single time we are going to pass a vector with size of this, which is going to be copied and passed, which is going to be very, very slow, like 10, 12 or something, very, very slow. To be efficient, instead of passing the vector, we can pass something else called reference. Is the term familiar, Duman? Do you know what is reference? No. You will learn it during this lesson. So, let's read first. A function packages a piece of logic behind the name, so you can reuse it and reason about it is in isolation. Yeah, you already write them. This section is about the details that matter in contests. Yes. So pass by value versus reference. By default, a parameter is copied into the function, as we saw, for an int that is free. But copying a large, like int is just all one, it's nothing, right? But copying a large vector on every call is slow. Passing by reference, which is this, works on a callless original object, not the copy. Use const reference when the function only needs blah blah blah. So let's see. So when we say like vector way, when we say vector v, what is this, right? It's a type of vector. In the whole memory, it has start, and then it continues on to some point. Doesn't matter what. What is important is the start. In the whole memory, let's say line, like not just like the vector, but in general, the memory is one huge memory, and then the variables, the type, and everything. We assign small pieces of the memory to those things, right? So how do we access the, I don't know, like the E? We have a starting point over here, and then we are able to change our indexation index based on the starting point and then how much we have to move. And then we access the element, right? So when we say we want to pass a vector, what it does, it just copies the whole thing and then it just gives the whole thing like very bad. But then the reference passing is basically you pass the knowledge that you have over here. Like the memory doesn't disappear, you have still the memory. The thing is that because this is like local, you can't really access it, right? It's not a global parameter. But then you can pass the memory, sorry, not the memory. You can pass the reference, and when you pass the reference, you can access the beginning. You know, you already have information. Like you only, if you say, for example, instead of like copying and like giving the whole thing, you say I have a vector starting from this point, being like length of this, blah blah blah. It's just again all one, right? So what it means, it's that for example, no copies can modify the original. So if you pass just a vector, it copies the whole thing and you have a new vector and you can do whatever you want. But if you don't want to make another copy, and if you want to make changes on your vector, the original one, you pass the reference and you access the vector directly on the original memory like place. No copy, and you can modify your thing. As for example, let's move over here. Function. So here, when we do this, and then let's say we have another vector like one, or no, let's say we have this, we have this, we have like until the end. Let's say we just input sorry, we input like let's say n elements, and then we pass the vector to this thing, right? And then we call like function v. And the function is supposed to change, like add 2 to everything. And here we do like and then we change the whole thing like as if we were to do the regular thing again, let's see what happens. We try to output the whole thing, right? Let's see what happens. So in the function we are calling, we change everything by 2, add 2, but it doesn't change here, right? So in the function it changes, but it doesn't change here. Why? Because we have just a copy of the vector, and it to be, let's say, changed, we have to return the vector which is already like which we just changed, right? We have to have vector in here so we can like return a vector, and then we have to assign the like this. It works, right? But it's very horrible, like so not only it copies here, but then we also return this, and then we like assign this. It's like 2 times ON, which is bad. So how do we fix this? For example, with the reference. So when you pass the reference, let's say we don't return anything so far. It's just function without any return, and then we don't change anything here. So we just pass the vector, and then call the like in the function we change everything as it, like the only difference with the first option with the first example was this, like the reference thing. And then let's see what we get. 3 1 2 3. As we can see, we passed the reference, and then everything here that's happening is happening on here, on the actual original vector. Is this clear? Demand. Is this clear? How it is changing the original when we get the reference? So if we don't do with the reference, it just copies the vector and then passes, right? And then every single change here is just done on a new vector which is not connected to the pass, right? Yes, but then if we do it with the reference, we just pass the location of the original one without any copying and anything, and then later on any operation is not done on the copy, it's done on the original. So with that in mind, this is already way more faster, it's so much better, right? But then also if we have read only needs, as we don't really have to let's say change anything, right? For example, for the sorting algorithms, we do not, like if we have, like if you write operator, right? How do we do that, right? Let's see. Do we know how to write operator? Like if you want to sort the vector, but not in the increasing order, but then decreasing, but not use additional on to reverse it. How do we change the pattern? Any ideas? Come on. Let's see. I don't know. Okay. So let's see. We get like n again, right? And then sin n. Also, if you want to speak like as a microphone, do not feel shy to do so. If you okay. And this, right? We just input the vector. Okay. And then when we do like a sort, right? Right? So it's going to return the normal order, right? Yes. So exactly. So how do we make it like different, right? So for that we can write an operator. Operator is in this case the logic that how like sort everything, right? So for example, we can do another comma here and then name the function of our operator as, for example, like it's like different way. Let's call it different way. And then for different way, like for the operator, we write a function. The function looks like this: bool, the boolean type, and then different way. We call it different way, and then and then the function, the way it works is that it gets two integers, in this case integers, because we are doing like sort on a like vector with integers, right? It gets two integers, and then it like integer a, integer b, right? Int a, int b, right? And then it returns as, for example, like if you want to make it decreasing order, like this. So return 1
in the cases of your let's say condition being true, and return 0 in the case of your condition being 0, and then the whole sort thing will happen on its own. Like the whole algorithm will happen on its own. We just choose the, let's say, the way they sort it. As for example, like the increasing order, if we return like true 1 when the A is greater than B, that means that it's going to sort everything in this way. Right? But then there is a problem. Is it going to work? No. I don't think so. Let's try. Well, it works. it's right? It works. But what's wrong with it? So instead of, nothing is wrong, but then it's not the efficient way, right? In this case, we don't really lose much, but then let's say again the reference, right? Something, same thing. Yes, the reference. Instead of doing that, we just put the reference here. It copies, yes, but it's not necessary at all, right? Like it's not necessary at all. Again, it works the same. Yes. And then, let's say, what else can we notice? We can notice that while doing the sorting, we do not necessarily need to even change anything on the vector, right? Like the operator by itself is the logic behind of comparing. The changes are done by the sort. So this function doesn't change anything. It just compares and it says like, oh, do whatever, right? So for this we can also have const. It makes even better. This is the best that can ever be. Like const and reference. So you cannot modify and prefer for big inputs. No copy, cannot modify. Passing by reference is also how a function effectively returns more than one value or modifies an array in place. Yes. So yes, that's this. Any questions about operators, about so to basically this is the way to write an operator for sorting, right? And here we saw that we use like constant the thing over here, reference, to pass everything fast as possible. And then let's talk about lambdas. A lambda is an anonymous function you can define inline, basically in the code like this. Invaluable for custom comparators and small helpers. This part is the capture list, which outside variables the lambda can see, basically. So here, let's see, the same thing can be done over here this way. So instead of doing this, we just do this. Let's see, what is this? The way we do this is, let's write it from 0.
like a sort, we begin, we end, right? And then instead of writing the function over there and doing everything like us and then calling the function over here, we just do inline function as this A and B, and then return A and B. Right? Does it make sense? Here, like in the function, we cannot access anything other than arguments, right? But then if you write, for example, like this, here we can see like int k out of this, blah, blah, blah. And then if we write this thing over here, captures everything by reference. Everything is captured by reference. You can access everything here, as for example k, which is just an variable, because we have this over here. So yeah, take a look over here. Inline function, basically. Good. Without name, without anything, just inline function. Let's see what else. This is it, and then let's. Any questions about this? No. Good. So let's talk about recursions. Do we know recursions? Or are we very new to the recursions? You can skip recursion, but you can't introduce it for the recording. Okay, so the recursion is a function that calls itself on a smaller input. Stopping at the base case. Every recursive function needs two things: the base case, when the function stops, and the recursive case, how to shrink the problem. So, for example, let's calculate the factorial. The factorial with recursion, with function, right? So instead of doing like a for, like a loop, and then calculating it without this, how we do it is like we have a function, like for example int func, and then blah blah blah, and then this, right? So here we have like int n. This is like the get the factorial of n factor, right? And then how we do this is like we have the base case, right? Which is like if n equal to what? Equal to 1, right? Or is it? Yes, exactly. Or like smaller than small or equal than 1. Right? If it's smaller than or equal than 1, we do return 1, right? This is the base case, like the thing that we know, which one, like the definition of the factorial, right? The very base case. But then, in case of n being bigger, what we do? We just shrink the problem down to a smaller problem, right? So, for example, if we have like an n over here, right? And then this n, the factorial of n, is equal n minus 1 factorial times n, right? But so to calculate this, we can just know this and then multiply it by n, right? But then we don't know really this, right? But so what do? We just return, we call the n minus 1, n minus 1. And this works because imagine this is the n, right? So we know that this is like n minus 1 times n, right? But we don't know the n minus 1. So we do this. We go over there to the n minus 1. We know that the factorial of n minus 1 is factorial of n minus 2 times n minus 1, right? We call n minus 2 factorial, right? And then the same thing works for the n minus 1, and then we call the same thing. It recursively calls until it reaches the point of the base, which is, for example, 1, right? So here we know that the factorial of 1 factorial is equal to 1. We return 1. So we have 1 returned over here, but then it, like here we wrote that like with the same logic over here, the answer is time, like the n times the thing that we just got as return. So 2 times 1, right, which is 2, and then here we return that, and then here we get 3 times the return, which is 6. The return was 2, right? And then we return this. This is the factorial of this, right? And then the factorial of this. This is the it is factorial of this times the n, which is 6 times what? 4, 24, and so on, so on, so on, so on, so on, so on. We just continue until we reach back to n, and we get the factorial of n. This is the principle of recursion. So again, the function calls itself on a smaller input. As for example, in case of factorial, n was a big input, and then we call the smaller version, which is n minus 1, until the smallest version that we can answer easily, which is the return 1 case. Basically, the recursive case, when we choose to shrink the problem to more smaller problem, and then the base case when we already know the answer, right? The same as the like mathematical recursion, but maybe the same logic. So, and then the call stack is also important to understand. Each call gets its own frame with its own local variables stacked on top of the caller. So let's see, as here, this, when it calls function, like func n minus 1, it does not change anything about function n minus n that was called before. It just calls a new one, completely independent from the previous one. And then the new one calls a new one, independent from this one and from this one, right? And then it calls a new one, it calls a new one, it calls a new one, and then we have so many functions in a stack on top of each other. This was the base case. This was the base case. And this is the later on a common case, n minus 1, and so on. When we build the whole thing over and over. And then when we reach the base case, we have the answer. We return the answer to the small, like the bigger case, and we get rid of it. We get rid of it from the stack. Like basically, the get rid of part is that when we leave the function, it just disappears, right? And then here, this one, when it finishes, it returns the answer to the bigger case, and then it disappears, and so on, 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 until the actual function. So it builds up and then builds down. Let's also talk about, for example, Fibonacci. How can we find Fibonacci numbers with recursion? For example, like this, right? So question to the month, for example, as long fib how was it? If n small equal 1, return n, right? Otherwise, return Fibonacci n minus 1 plus Fibonacci n minus 2. Duman, do you think there is something wrong with this approach?
Can you explain why? Like why can it blow up in large N? Yes. So the function by itself is not wrong, right? It works correctly. It gives the correct Fibonacci number. But there's a catch. And the catch is that, for example, here you can see that n minus 1 and then n minus 2, right? From one stage, we divide it into two parts. And then for this case, it's going to also divide it into two parts. N minus 2, n minus 3. And then from this case, it's also going to divide into two parts. N minus 3, n minus 4. In this case, it's also going to divide into two parts. N minus 3, n minus 4. In this case too, in every single case it's going to divide into two parts unless it's the final base case, right? So in that way, we can see clearly that we have so many repetitive patterns, so bad. For example, n minus 3 here, n minus 3 here, n minus 3 here. We compute n minus 3 times already. And then if we go deeper into our tree, we would see that the number of, for example, n minus c something, like big number, is so much more, because it is computing everything without like regard to if it was already, let's say, if the number was already answered or no for the some x. And then it is just 2 power of n.
but even recomputes the same values over and over. Its recursion tree has about 2 end nodes, so it is exponential. We fixed that in section 5. That is correct. So also we have to watch out for a missing or wrong base case, because otherwise, like our recursive call that does not move toward it means the recursive never stops. Or infinite recursions that overflow. Oh, sorry. So basically, if the recursion never stops, or if it's infinite, it is going to infinitely recurse itself, and then by the end just overflow the call stack and crash. Also, we have to keep in mind the depth, as going too deep can also blow the stack. As for example, because as I mentioned over somewhere here, we have everything stacking up on top. It's not like we go somewhere and then the thing disappears. No, we go, reach the end, and only then it disappears, right? So if it's too long, it can just overflow. Let's talk about divide and conquer. We are not going to cover very, let's say, deep. We are not going to cover very deep divide and conquer examples. Like by itself, the algorithm can be very interesting and complex. Some solutions can be very difficult with this, right? But then today we're going to cover the idea of divide and conquer. So the divide and conquer solves a problem by splitting it into independent subproblems, solving each recursively and combining the result. A very vivid example of divide and conquer is merge sort. It's the classic, very vivid example of divide and conquer. So merge sort is an algorithm to sort, right? So the way it works is it splits the array in half, recursively sorts each half, then merges the two sorted halves back together. So over here we can see the base case, 0 or 1 element is already sorted, which means we don't have to change anything, right? If it's only one element in a place and it's already sorted, or if there are no elements, it also means it's sorted, right? So in that case we don't do anything. But then after we get the middle part, right, with the like with the same length from the binary sort, we get the middle, and then we do merge sort. We call the same function again. We do recursively. We call merge sort for the first half, as for example, low mid, right? Low mid. And then we merge sort for the second part, from mid to high. And then after we sorted first and second halves, we do merge, combining them, and the merge is linear time merge. There is a way for that. Its running time follows as recurrence. Tn to Tn half plus On. And we spent On work on doing the merge, each level. And there are n log n levels because it halves every single time, which gives us complexity of n log n. Let me show you to make it very clear. so this is the whole like array. This is the first half, this is the second half. This is the first half of the first half, this is the second half of the first half, and so on. Like we just divide the whole thing into parts, right? Does it make sense? Yes. And this is actually how the merge sort works. So it divides, it goes first here, and then it divides, it goes first here, it goes first here, it goes first here. It sees the thing, it goes back. Oh, what? Oh. Okay. I didn't expect an array appearing. Anyways, so then after it goes here and it connects. It takes ON with a very small size, right? And then it goes back. It goes here. It goes here. It does this, and then it goes back. It goes this. Basically, the main part is the ON part, which is the size of this. The size of this. This is the ONs, right? And basically, as we go lower, we get the things smaller and smaller. And at the end, the sum of everything is the actual area of the whole rectangle that I just drew. For example, like this is n and this is log n, and then we get n log n. Does it make sense? Nice. Recognizing a recurrence like this and reading its complexity of directly is a skill worth practicing. Binary search is the same idea with one subproblem instead of two. We just divide. But then here we just connect also. Let's talk about backtracking. So backtracking searches through all candidate solutions by building them incrementally. Choose an option, recurse to extend the partial solution, then undo the choice and try the next one. It is how you enumerate subsets, permutations, board placements, and paths. They include or exclude pattern from generating all subsets. Let's see. So if E equals N, cur is one complete subset. So N is the target size, and then is the index that we reached. And then if it's equal N, we just return, as we already get our vector. We got our permutation or something else that we're trying to build. But then if no, we call subset E plus 1 N cur. We push. Okay, let me see what. Yes, exactly. So we are trying to build sets, right? Every single subset of the set. So if we just go forward as E plus 1 N cur cur. Cur is the vector where we build our answer for each subset, right? N is the target length, like the amount of elements we have, and then the e+1 is the index, right, or something. Like, depends the problem. In this case, we just try to create the subset of like from 1 to n. That's why we don't have any vectors and other things. So if we do subset e+1 and cur, we just keep e. We don't add anything to cur. And in the later, every single recursions happening from here, from this point, are going to be excluded. Like, they're not going to include element e. Every single answer that we get, they are not going to include e. And then after this subset of the answers, we move forward. So we add e. And then we have subset e+1 and cur, basically continuing to build the vectors, but e already being included. And then after that, we backtrack. Basically, after we reach some point, let me show you on the more understandable diagram. For example, this. This is include, and this one is like to not include. Okay, and we have to choose to include 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have to recreate every single subset of the whole thing. As for example, nothing, and then 1, and then all of the like single ones, and then 1, 2, 1, 3, 1, and then like 1, 2, 3, 3, 4, 8, and then 1, 2, 3, 4, like I don't know, 3, 4, 7, 9, and so on, up to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, like the whole thing. So the way it works is it starts from 0, it starts to create the answer, right? So it is like, in front of a choice to include or not to include. It first chooses to, for example, include, and then include, and then include, and then include, and then include, and so on to this point. And then we get the answer. And after we get the answer, we get this out. We go back. And we choose the other option. To not include. And then we fix the answer over here again. And then we get this, we get this out. No, I mean, in this case there is nothing to get out, but let's say like it's not include or not include, but like other things. We change our mind. We change it. We remove it, and then we go over here. Let's say the problem can be changed into like, I don't know, creating a string of length 10, either being A or B, all of the possible options. As for example, A, B, B, A, or like B, A, B, and so on. So it's like either A or B. it's option A and it's option B. So after this, we get back from here to here, and then we go over here, we choose this, another option, another answer, and then we go back, we backtrack, and then after that, here the function is finished, like we went both here and here, and then that means that this is also finished. We backtrack this too, and we go over here. From here to here, 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 here. From here to here, right? So from here we checked already this, we checked the other way. And from here we check this way, we get answer. And then we backtrack. We go back, we go here. We get answer. Okay, we get back here. We already went there and there, so we go back over here. So here we already went there, and then we go over here, and then here, back, there, back, here, back, here. Oh, I couldn't start. Here. This is called backtrack. We create the whole thing by going, fixing, choosing, getting the answer at the very end as a base answer case, and then backtracking back to get the other answers.
Does it make sense? Nice. So this popback is the heart of the backtracking. After exploring a branch, you restore the state, so the next branch starts clean. After you added something at the end, you just get rid of it, so you can go back and then add something else, right? Permutations work the same way with a used array. The end query problem places the queen per row of resources. Doesn't matter. So something called pruning. It is what makes backtracking practical. The search tree is enormous, right? So cut off branches that cannot possibly lead to a valid solution as early as you can. If we see that it doesn't answer to our question, it doesn't qualify as an answer, we just cut it, so we don't get for example 2 power of n or something. The early we cut the tree, the more we save.
But yeah, it's just something to think about. Nothing important. And it's very important to watch out for these things. Forgetting to undo your state. The pop back, if we don't do it, it's gonna be starting to be mess. It's without popping the 10th element, we would go back, assume that there is not an element, to add another 10th element, 10th element, but then we forgot to pop the 10th element, and then we add another thing on top, and it's just completely wrong. This is the single most common backtracking back. Every change you make on the way down must be reversed on the way back. Okay, if it makes sense, we can continue. So from recursion to memoization. Memoization can be seen in case of the Fibonacci, right? So in case of Fibonacci recursion, we just saw that we were repeatedly repeatedly counting the answer for the same number Fibonacci, like n minus 4 would be counted again, and that's why we have like 2 power of n complexity, right? But then with memoization, let's read. The waste is clear once you picture the recursion tree. Fib1 computes Fib3 twice, Fib2 3 times, and so on. The fix is a memoization. Remember each answer the first time you compute it, and look it up thereafter. So here we have an array called memo, as memoization, and then in the Fibonacci we check the base case is like return n, right? If it's n is less than equal 1, and then after we check if the memo n is not equal -1, we return memo n. So initially everything is -1, means we don't have anything already memorized, like we don't have anything already known there. And then here we check if it's not unknown. We already have completed the whole process and we already know the answer for this. Then we just return the answer without going again to the same thing. But if it's not the case, we have to compute. We have to search for the answer. So we return the formula. We return the Fib n-1 plus n-2. The same recursion, the same exact recursion. And then we also assign memo n to Fib. So we assign the -1, it was -1, but then we assign it with the actual Fibonacci number. So after we finish this, after that, when we encounter the same n, it would not be -1, it would be the answer already. So we would only need to get the answer from the already stored array, which would be 01. So each value is now computed once. So this is ON, right? Recursion plus a cache of subproblem answer. Sorry, recursion plus a cache of a subproblem answers is a dynamic programming. Exactly. You have just written your first DP. I mean, solve, and that is the direct on ramp to the next topic. And then also we are going also to talk about DFS. We haven't learned DFS yet. The next topics, like the next class, is going to be fully about graphs. Let me tell you, it is going to be about the graphs, graph terminology, nodes, edge, and then BFS, DFS, trees, and so on. And then we need to understand recursion and everything to be able to solve later on coming graph problems and algorithms. Any questions about memoization? No. Very nice. Very nice. Very nice. So you can do further reading over here, Yusako guide, or do practice problems and stuff. Yes. From this point, basically the whole course is going to cover very nice topics related to many topics are related to graphs, which is nice. So yes, I'm going to also share the problem sets lately. someday, maybe today, maybe tomorrow, we'll see. And then start to collect the problems that actually are like for practice, because so far you can only practice from the PDF, which is not as convenient, but anyways. So yes, thank you very much for the class. If you don't have any questions, that's it.